Okay, so good morning. Uh, Let me first briefly review what we have discussed about uh, a very small dipole antenna, how it read and uh, how we describe it mathematically, the property. You see, because this is a very fundamental things for understanding antenna working principle. And if you're interested in anything about antenna design, and this is the foundation. Okay, so let me very quickly review this, and then we continue this subject today. Right. So first, what we uh, assume we have a very small dipole. Okay, this small dipole, the overall length, the length is so small. The length is much smaller than wavelength, and usually, okay, that L should be smaller than, let's say, 1/50th wavelength. Okay, so it's very small. This is one. This is one assumption, and the second assumption, okay, is constant current. Okay, so we assume the current is constant. Okay, and then because for a long wire antenna, if we chop it into many small pieces, okay, and then even though you have a certain current distribution, but over a small section, as always I can assume this is a constant current. So what we are looking for, what we are looking at, is a one of the very small section of a large antenna, right? Okay, so that's why I said this is a foundation, right? Okay, then also you see another assumption, very thin. So that means that the radius is so small compared to wavelengths we ignore, right? So under these three assumptions, we describe how antenna radiate, right? And how we consider the antenna, the radiation is we already derived a vector potential vector potential vector potential A. How vector potential A is defined? The A is defined by two things. Okay, one is curl equal to B, right? Okay, and also we justified. Okay, we also have another definition to define is divergence. We were going to say the divergence of A, right? Okay, then we also find how to find the A potential. Oh, we say the A potential is, okay, very similar to the static case, is we have a current density, okay, then so we need to consider, okay, we need to consider, okay, let's consider a scalar case, okay. We need to consider the time delay, okay. Then this is R, then we do the integration over a vector over the source. And what R is, the R is the distance between the field point and the source point, right? Okay. This is how we find potential A first. Okay, we assume the current, okay, we assume current constant, then we substitute this current into the general formula to find vector A, okay? And because the current segment is so small, okay, it's so small, we can easily find vector A, okay? We can easily find vector A in this form, okay? And then you only need to take a few minutes, you can derive this, so we don't repeat this, okay? Once you find a vector A in a coordinate system that basically described in XYZ coordinate system, because I put the current along the z-axis, then I use the transformation. I use transformation to convert the Cartesian coordinate, the solution in Cartesian coordinate system into spherical coordinate system, okay? So this is simple matrix manipulation, okay? This transformation is given, okay? It's given. Then we find the A vector potential in spherical coordinate system. Then we use one of the relation between magnetic field and the magnetic vector potential function A. We can find magnetic field H. Okay, this H is created by current. Okay, by the current on the antenna, right? And all this manipulation is just what we have learned in calculus. Okay, and we urge every one of us do this exercise, right? Do this exercise. So once we find the magnetic field, okay, once we find the magnetic field, okay, then we can find the scalar potential function. That is another relation to define vector potential A, right? So this is how we use, oh, sorry, in the class we didn't go this way. Okay, in the class discussion, we jump into this relation. This is the Maxwell equations, right? This is the Maxwell equations, the Faraday's law. Oh, sorry, this is Ampere's law. This is Ampere's law, right? And you see, because we have a current we call displacement current. So this current equal to j omega epsilon times E in time harmonic field. Then this tells us if you know magnetic field, you know electrical field, right? And then this also, we need to use the curl of a vector, okay? Curl of a vector field, and this we already gave a general expression. We already gave the general expression, this, right? Then we find the total field, total electric and magnetic field. We find the magnetic field, we find the electrical field, okay? This is what we have done, right? And I left only one problem in last week as assignment and ask you to practice to find electrical field using scalar potential function. This is another way we can find electrical field, right? So we find vector potential A, then we use this relation we call Lorentz condition. We call Lorentz condition. We find scalar electrical field potential function. Then we use scalar function and a vector, a scalar potential and a vector potential, and they are related to the electrical field. They are by this, okay? This is always true. This is the first principle. This is always true. And then we can find the electrical field. Okay, this is assignment I uh, uh, I gave last week. Right? If you derive this using calculus, first time you may not get the correct answer. Then go back to find where you made mistake. Okay. The second time and third time is the time you gain most. Right. Okay. This, this is what we have. This is what we have done. Okay. Now let's come back to the subject today. Right. Before we continue that discussion, we just quickly review. Okay. Let me review the Poynting vector. Okay. The Poynting vector theory. Okay. Right. We had learned the Poynting vector theorem is if we have a current in a system, okay, then if we have artificial surface S, okay, so S, then the normal, this is normal direction, right? So we can define a Poynting vector which is E cross H. This stands for a power density at any location, how the electromagnetic field, in what direction that energy goes. Okay, right? So this, if we do the surface integration, closed surface integration, okay, that collects all the flux. You see, because I have a dot product with a differential area, then that means I'm calculating the net flux. Okay, I'm calculating the net flux, right? So that equal to the total stored electrical energy, magnetic energy, and plus the energy consumed on the loss, right? So we prove this we call a Poynting theory, right? Now let's discuss how to describe this Poynting vector, because Poynting vector is so important. Poynting vector is so important, which stands for the power, the energy, the density, and what direction it goes. Okay, electromagnetic field, right? And also when we define this P, I should emphasize this E is a function of location and also function of time, and the same as magnetic field. Okay, at the same location, at the same point, at the same time. Okay, this is general expression. But we said to say in electromagnetic analysis, we always prefer to use time harmonic. Okay, time harmonic field. Okay, so fields. Okay, so in time harmonic field, we assume the time change, the change with time follows the fashion is constant frequency, constant frequency, right? So if you have a certain initial phase, I can accept, okay? And if you like to consider how it changed with the distance, if you travel in the direction of that, right? So this is how we describe a wave, okay? How we describe a wave. This is we call, by having this, right? Then we define a phasor. Okay, phasor is a vector, and the phasor is a complex. Okay, then that has a magnitude. Okay, magnitude that has a polarization direction, and this is a phasor, then change with time, then I take a real part of it. Okay, so this we call is a phasor, right? This is a phasor. Oh, sorry. This is this with a certain magnitude. Okay, and also you have a polarization direction. Okay, so let's say in x direction. Okay, in x direction, right? So we use phasor. Now let's see how we describe Poynting vector using phasor field component. Okay, let's say capital E and capital H. Okay, this is E is, I don't know how to write this. Okay, the E, so this is a function location and the time. Okay, this is a function of location. Okay, let's say E. Okay, right? Okay, this is also a vector, right? Now, when we consider the time harmonic field, okay, this E is described by a real part of this, right? Real part of this. And I rewrite the things inside the bracket, I write in, and also take a real part. If you take a real part, that's equal to this, right? So this means complex conjugate. Complex conjugate. So what that means, if E, I have real part and imaginary part, the conjugate is real part minus imaginary part. Okay, so that was what the conjugate means, right? And then very easily you can justify this equals. Okay, then when we calculate a Poynting vector according to first principle, that is the time, that is function of time, right? The first principle, then that equal to, because E is E, right? Okay, E I can write into this form, and the magnetic field I can write in this form. Okay, so therefore we can easily justify for time harmonic field, if we use a phasor, because this is a phasor, right? Okay, if we use a phasor, that equal to this. Okay, that equal to these two terms. This term phasor itself has nothing to do with time, And the second term has something with time, but frequency doubled, 2 times omega. Okay, then if we calculate, because this is instantaneous, this is a function of time, this is instantaneous. So if we do the integration, okay, over a whole period, okay, the total power, which is a function of time. If we do this integration, first term has nothing to do with time, right? So the first term equal to t divided by t, right? And then this is first term. The second term is something, okay? Something, if you want to do the integration, something related to cosine 2 omega plus a constant phase. Okay, plus constant phase with time. And what is the T? T, 1 over T equal to frequency, equal to omega divided by 2 pi, okay? If you do this integration, because this integral is a function of cosine 2 omega, this integration is constantly equal to 0. You can verify this, okay? So the second term of integration is always equal to 0, okay? And we are not interested in the power density at a certain time instant. We only interested in the average power density over one period, okay? The T. T is period, okay? T is a period, right? So 1 over period. So therefore, now we have to get used to this. When we describe power density using phasor expression of electromagnetic field, okay? We don't use E cross H. This is not correct, okay? This is not phasor, this is not phasor, this is not phasor, this is not phasor, okay? This is a function of time, okay? But if we use a phasor, we have to use E cross H conjugate. And don't forget this 1/2, because 1/2 coming from here, right? This integration, we have this 1/2, all right? Now we have to get used to when we use time harmonic. Just now we reviewed how we look at a very small antenna. We analyze it using phasor concept, okay? Because we don't have time. We don't need to deal with time variables, okay? It's much more convenient. This is the solution we just obtained, right? This is solution we obtained. We got magnetic field, we got the electric field, okay? This is exact solution. Okay, exactly solution. Exactly solution is not easy to come by for electromagnetic field, except those very, very small or very, very small class of classical problem, okay? This is one of the classical problem. If you learn electromagnetic theory, if you don't understand how antenna read, don't tell me you take my class, okay? Don't tell people you have ever learned electromagnetic theory, okay? Now we have electric field, we have magnetic field. Let's take a close look. Let's take a close look. So for magnetic field, we have something related to 1 over R, right? Because this is 1 over R component terms. We also have a 1 over R square terms, right? Because R and R, okay? And look at the electric field R component. We have R square, we have R cube, okay? And for theta component, we have 1 over R, R square, and R cube, okay? R square and R cube, right? So this is a very interesting question, okay? This is a very interesting question. We have to look at how the field change when the distance change, okay? Because our observation point, okay, if the antenna is located here, this is our observation distance, R, okay? This is antenna, okay? Antenna, I change the color. Okay, we have antenna, very small antenna, right? Okay, so we read it. Then once R is very, very smaller than wavelength, okay, you see, because this is all K multiplied by R, right? So K multiplied by R means 2 pi, K is 2 pi divided by wavelength, R, okay? If I look at this, I look at R, I always measure the distance in terms of wavelength, okay? I measure distance over wavelength. If this is much smaller than wavelength, then which component is dominant? So of course, high order terms dominant, right? High order terms. Then you can check. One is 0.1. One is 0.1 square. Okay? Which one is larger? So of course, this is much larger than this, right? So therefore, if we look at, if this field change with 1 over R square, the distance, okay, once the distance becomes smaller and smaller, one of observation point closer and closer to the antenna, the field component is significantly increased, right? But also on the other side, okay, on the other hand, when the distance is larger than KR, larger than 1, this attenuation speed is much faster, okay? It's much faster than 1 over R terms. Okay, this is 1 over R terms. So the dividing point, let's say dividing point is KR equal to 1. Okay, so when KR equal to 1 is very interesting, right? So the real, for the magnetic field, okay, the real part, this is imaginary part because we have G here. This is imaginary part. So this become real part, right? They're equal. Okay. The similar observation we can say. Okay, similar. And we call this KR. We have a word we call radial distance. Okay, we call radial distance. So we always judge by this. Okay, so this is what I said. When the field is very close, when the field is very close to antenna, and then we have both magnitude, or we have both real part and imaginary part. Okay, real part and imaginary. We are going to look at how that affect the power. Okay, how about power? Because only look at the field, it's not very clear, right? Okay. Then we have a very special case. We have a very special case is if this KR is much larger than 1, okay? When this is much larger than 1, we can omit this term, we omit this term, right? Okay, and we omit the whole thing because this is 1 over R squared, 1 over R cubed, right? Compared to this is much, much smaller than 1 over R times. Okay, this is how we grab the most important things. Then we ignore the insignificant terms. This is a very important things in engineering. Okay, in engineering, the difference between engineering and science is we know as engineers, we know how to seize, how to catch the main factor, okay, the issues, right? So therefore, the ER component is completely zero, okay? And how about for magnetic field? Magnetic field we omit this term because this is 1 over R squared, right? So as a result, okay, for near field where this radial distance is much smaller than 1, okay, the high order term high order terms dominant. Okay, high order terms dominant. Then, if you look at the power density, okay, that power density is not a complex number. When we look at the power, that means that is effective power. People can receive it. Okay, people can receive it. Right? Then the power, we take E cross H conjugate, take a real part and divide by 2. Okay, then we have all these field components in hand, right? Then we can clearly say, okay, after you see, because we have a real part, we have imaginary part, and so on. But after you multiply E cross conjugate H, you have everything is imaginary part. Okay, so that means the real part is 0. Real part is 0. So that means the electromagnetic field nails the antenna. Nails the antenna. You don't have power. You can transfer. Okay, power. You can find the power. You can transfer. All the energy is stored energy. Okay. Then where is this energy? Where's the energy you can find? You say the power is. Let's look at the far field. Okay, in the far field, under this assumption, we only have 3 field components. Okay, we only have a 3 field component. Oh, sorry, only have a 2 field component. Sorry, only have a 2 field component. One is electrical field, one is magnetic field. And the electrical field only has a theta component. Okay, theta component. Magnetic field has a phi component. All right. And this theta component and the phi component in the coordinate system, this is that. So this is a phi component. And that is magnetic field phi component. Okay? Then these two perpendicular to each other, right? And also they are perpendicular to the direction of propagation r, right? Now we have a picture now. What is this? This is what we learn plane wave, right? So you say, no, in plane wave, Professor Wu, you teach electrical field is in X direction, and the magnetic field is in Y direction, and the propagation direction is in Z direction. Yeah, it's up to you, right? If you like to call E theta component is X, and the phi component is Y, R component is Z, this exactly is this, right? Okay, so this is what we said is no matter how large or how small your antenna is, at a very far distance, and how far it is, okay, there is a rule, okay. So how far it is the largest dimension of antenna divided by wavelength and times 2. Okay, if the distance is larger than this, we call this a far field. Okay, so we don't have time to derive this, but well, we are going to discuss this in today's ESTR class, and how we derive this condition, right? Now, what the D is the largest dimension of antenna. Okay. So if you are interested, you're welcome to join this class. start from 11:30, right? And still in this link, okay, in this room link. Okay, so all right, it's very far distance, the field, okay, you can consider as a plane wave. You see, because we can say E theta divided by H phi equal to wave impedance, right? Both E and H perpendicular, and also E and H perpendicular to the direction of propagation, right? Okay, but interesting thing is we know how the antenna radiate in all the directions. In what direction you receive signal most, and in what direction you receive nothing. Okay, you receive nothing. This is what we call radiation pattern. Okay, we call radiation pattern. You see, if we have antenna placed in that direction, this function, if you plot this function, you see this function is only function of theta and constant in phi direction. So if you cutting at, you say, at z equal to 0 point, this is constant, circle, it's a circle, right? But if you cutting at phi equal to any angle, right? So that looks like that antenna, okay, that looks like this, like a donut, okay, like a donut shape, okay, right? Then you can say the antenna, if placed along that direction, then the radiation in this direction is minimal, and also in the bottom is also minimal. Okay, so sometimes you say people come to talk to me and say, "Oh, Professor, I'm very anxious." I said, "What? Why?" They said, "Oh, there is a base station antenna installed on our rooftop, okay, and we are worried about, we are concerned about the health, right?" And I said, maybe you say the location right underneath the antenna is the safest. You see, because nobody want to radiate the antenna, radiate your energy to the sky or to the ground. There's no custom, right? And then also, if you have a dipole antenna placed like this, at this direction and that direction, you see, no energy really, zero. Okay, 1 theta equal to 0, 1 theta equal to pi, 0, right? So no energy really. Okay, now let's look at the power density and the radiation. We call radiation resistance. Radiation resistance. What is the radiation resistance? Radiation resistance means its ability to radiate energy out. And then because the people not familiar with field, electromagnetic field, if people not lucky, not get a chance to take my class, they may not know EM theory, right? So I'm just joking. So people may understand better about the circuit theory, okay? Can we describe antenna problem in the language of circuit theory? Okay, this is the question I like to answer. Okay, let's look at the Poynting vector, right? We have a Poynting vector in phasor, E cross H conjugate, and then blah, blah, blah. So we multiply by this, okay? Then what we have, we plug in all the total field. Then we can say, the real part, oh, sorry, not the real part. Because this is vector, right? This is vector, not the real part. This is vector. The vector, we have two components. One component in R direction. This is in R direction. This is in the power flow in theta direction. Power flow in theta direction, power flow in R direction. Okay. We know in theta direction is really useless, right? In theta direction, what is turning around your antenna. This is not what we want. What we want is the antenna, you really toward outside, okay, outward, okay, outward directions, okay. Then we can say if we calculate the flux of a complex, this is complex power, because you see we have a real part, we have imaginary part, so this is complex power, okay. Complex power, you say what do you mean complex power? Complex power is not new, right? I think in circuit theory, you also need to adjust what is complex power. Okay, complex power means you have real part, which is the power, real power. Okay, another imaginary part, that means the power that's stored energy. That energy is stored by inductor, by capacitor. Okay, and then you have a couple, mutual coupling, and so on, right? And also you have a mutual coupling capacitance. Okay, so that's stored energy, that is imaginary part. So imaginary part to us, it is physically exists, but very difficult to use. Oh, I cannot say it's very difficult to use. You see octopath, that completely using near field. Okay, that completely using near field. You can induce a current on another, say you have inductor in the near field. If one put another inductor, you have a mutual coupling. Okay, so if you have a mutual coupling, if you have a current I1, then you have a current I2. Okay, this is induced field. This is not a radiated field. Okay, so I have to quit. Then we have real part, we have imaginary part. Okay, the outward. So what that says is, okay, the real energy go out is only the R component. Okay, this R component, we have the real energy. We are talking about the R component. The real part, the energy has we have a real part. Oh, sorry, we have a constant part, because this is already integration. It's not density function. It's a total energy go out. Okay, that is constant. Giving antenna, giving current magnitude. Okay, how much power it can go depend on how much current you give and how large. You see, one determines the current and also determines the length divided by wavelength, right? How long? Longer your antenna, more energy you can radiate. Okay, right? This tells us this. And the imaginary part power will decay so fast because that proportion to R cube, 1 over R cube. Okay, decay very fast. Okay, then we can say once the distance is little bit larger, we can ignore this. Okay, we can ignore this. So let's just ignore this part. Okay, we don't have time to discuss this. Then let's look at the real part, right? So the real part we said is equal to this. This is total power radiated. Total power radiated, right? And then if we use a circuit theory, okay, let's say we have resistance. Okay, we have a resistance, we have the resistance, we have a current. Okay, this current change with time. Okay, this is the change with the frequency. Okay, so that means instantaneous current. Okay, what is average power? The average power. Okay, the average power, the power average Okay, right? One half, where does the one half come from? Also, time average. Okay, so if you forget, go back to review your circuit theory textbook. Okay, you must have this one half. As long as the voltage and the current change according to cosine omega t plus phi, right? Because you don't have time delay, okay, with traveling distance. It's not a wave, okay? You always have one half, right? So that means if the antenna system I treat it as a circuit, the power radiated, okay, I treat it as a resistor that absorbs the whole energy radiated by the antenna. I can equal this too, right? You allow me to extend this, right? Then we can find the resistance, the equivalent resistance equal to this, equal to this. This is a very classical result for any antenna people. They must understand. If you have a very, very small dipole antenna, okay, very small dipole antenna, its radiation ability is measured by radiation resistance, okay, radiation resistance, and then this is 80 times pi square. Don't forget, this is a wave impedance. I already repeated 100 times. Okay, if not 100 times, at least tens of times. Right? This is 120 pi. Okay, this is a intrinsic wave impedance for plane wave travel in free space. Right? Okay, so we have now. I hope we have a clear picture how plane wave is created. Okay, how plane wave is created, right? And then we describe what is the real energy, what is imaginary energy that relate to the stored energy, right? Okay, then we are interested in, for antenna, we're interested in the real energy that can propagate, okay, along far distance, and also real energy that attenuation factor is 1 over r. For field, okay, for power is 1 over r squared. Okay, we stop here today. And Tan Xiao, is that correct? You say our ESTR still in this room, right? In this room class.
Okay.
All right. Okay. If any one of you like to join, and we are going to discuss is to discuss how we decide what is the behavior of near field and the far field, where the boundary is, how we determine the boundary. Okay, because that is very important when we measuring the antennas. Okay, because when we measure the antenna performance, we always measure in the far field distance. Okay, and how to determine the far field distance. Also, Tan Xiao, I think that may also help you. So you can also join our discussion. So I already put that notes in your job box. Okay, so let's stop today. So don't forget sending your high check, high comment. And if you like to discuss with me about anything about the middle term exam, and then I will be here. I'll be around in this Zoom session. Oh, okay. The middle term, uh, okay, I will check with, Tan Xiao, do you know what is the progress for the middle term?
Sorry, what? The average
Yes, I will.
is about 47.
What? 27?
47.
Sorry, 47.
Yeah.
Okay. Yeah, it's about 47. It's so badly?好像这个这个这个主要问题是什么？你给我拉一个 room 出来，你给我拉个 discussion room。
哦哦好。哦，我不是主持人。
哦，那我怎么拉呀？哦，sorry，我忘了这个事情。